Hello, my name is Daniel Thompson, and I'm an undergraduate in ECE 461, and this is my challenge assignment number 1. So I'm going to walk you through my code here. I have a couple of pound defines. These are for various variables that I'll use throughout the program. I have some variables here that I have for placeholders. I'll talk about those when we get to them. And I've declared 2 functions, and I will explain those as we get to them as well. So in my main here, I start off by holding the watchdog timer, setting the voltage, setting both banks to wait state. I'm setting my clock here. As you can see, I'm using the SMCLK clock, and I'm using that to init my watchdog timer to just about 1 second, slightly over 1 second, and I'll explain later why that is. I'm going to clear the LED. And I'm going to init some timers, so why don't I take you over there. This is my init timers function. As you can see, I'm using a timer A. I'm going to be using 2 different instances of it, A0 and A1. Both are going to be for 1 second. I'm also going to be using the SysTick timer, which is also going to be set to 1 second. And I'll explain how I use the 3 of those timers as we get there. Returning back up to my main, after I init the timers, I'm going to set that LED2 as my output, and then I'm going to configure port P11, which is the button, as an interrupt, and it's going to be my input. So before we start my always loop, I'm going to turn on timer A1. This is going to keep track of when 1 minute has passed, so I know according to the requirements that I need to be writing to flash memory once every minute. And we can go ahead and look at timer A1. It is right here. All it's going to do is it's going to increase the second count every time it's called, and then if it gets to 1 minute, it's going to clear the second count, and it's going to use the variable flash memory to indicate that it is now time to program the flash. So let's go back up to our main loop. The first thing it does is it checks, do we need to program the flash? It's initialized to 0, so we will right away, and it's going to call the function test flash. So why don't we go ahead and go there. This is going to be my main function for programming the flash memory. I start off by declaring a buffer, which is 1 sector long, and I'm going to store the hexadecimal value 0xDA, short for Dan. And then what we're going to do is we're going to unprotect all the sectors in flash bank 1, and that includes sectors 0 through 31. After the sectors have been unprotected, we're going to do a mass erase, and then what we're going to do is program each individual sector in a for loop that will go until we have programmed all the 32 sectors. After we're done, we're going to turn on our timer A0, and then we're going to turn on a green LED light to indicate that we've finished. Now the reason we turn on A0 is this is a 1 second timer, and if we go up and look at the code, all it's going to do is the first time it's called after 1 second, it is going to clear the LED, so that way we know that we've pulsed for 1 second. And then after we've pulsed, after we turn on our LED, which is right here, we're going to indicate using the flash memory variable that we have actually now we've already programmed the flash, so we won't need to do it again until the interrupt calls again. And then at the very end, we're going to reprotect our flash sectors, just as good coding practice. So if we go back to our main function, after test flash is called, we're going to check if the button was pushed and just enable the interrupt if it is. I'll talk more about the button interrupt in a minute. And then we're going to check the value hold count, and I'll explain how this variable increases in the button interrupt, but mainly this is checking to see if it has increased, if it has gone to 3 seconds, and if it has, we're going to enable our timer A0, and we're going to turn on a red LED. And this A0 again is the 1 second timer that will just flash the red LED for 1 second, indicating that we're about to start our watchdog timer, which will then turn on shortly after the LED has flashed, and it will reset the system. I can show you that running on my board at the end of this demonstration. So now I'll take you to my port 1 interrupt, which is the button interrupt, and I'll explain how the hold count timer works. So the first time the button is pressed, the interrupt is called at the moment the user presses down on the button. Then the button position is initialized to clear, so this will be called the first time. When the button is pressed, we will enable our sys-tick timer, and then we will change the way that the interrupt is triggered. It is initialized from high to low, which means the interrupt is triggered when the button is pressed. But after that, we're going to change it so that it's low to high. This will re-trigger the interrupt when the button is released. And then we will state the button position is now on. Now the idea of this is that when the button is pressed, the timer will start, and then when it's released, we will call back this interrupt, and it will come to this section of code where it will disable the interrupt, or it will disable our timer, and then it will clear our hold count. And then we will set the flag back to trigger the interrupt when the button is pressed. These will alter back and forth so that every time the user presses a button, it will time it, and then when it's released, it will stop timing it. And then we will also, after it's done doing this code, we will disable the interrupt so that it will have a slight pause after it's pressed. So that's it for the code. What I'm going to do now is go ahead and compile it for you, and we're going to run through and look at the memory addresses to see it being stored. I'll go ahead and so I've already set some breakpoints in my test flash function, so we'll go ahead and get it to there. As you can see, this is right before the memory is mass erased. So if we go ahead and look at that section in memory, we can look at this is where bank 1 starts, and it is where my program will begin to erase the one more zero. It will begin to erase the hexadecimal value, begin to erase the sectors. But as you can see, the system has already been erased because it was initialized from the beginning. So if we go ahead and put a breakpoint right here, as you can see, we erased the flash and it didn't change because it was already erased. But if we look now, we will be writing to the flash one sector at a time. So I'll go ahead and run it through one loop of this function. You can see that it does indeed go ahead and program the hex value 0xDA to that sector. And if we scroll down, we can see where that sector ends because it is no longer, because this memory has still not been written to. So if I have a breakpoint at the end of this loop, and we can go ahead and run to it, and we'll see that indeed all of the memory in bank 0 will be, or bank 1 will be flashed. And if we go to the last memory location, we will see that it too has been flashed. So we know that all of bank 1 has been flashed with, or programmed with this value. Now, according to the requirements, this function is to be called every minute. So I will go ahead and run this program back to where we will erase, which will be in 1 minute, and I will cut that out of the video, but I'll go ahead and get you there. Okay, so as you can see, we have returned to the same function right before the erase. And why don't we go ahead and check the contents of the beginning of our memory bank and see what they are. And they are still set to the hex value we wrote to them. So if we put a breakpoint right before we write to them again, we can run this, and we should be able to see them erase. And we can go ahead and check the end as well. And we see that it was all cleared. I will now demonstrate the use of the watchdog timer on my board and show how the memory does indeed get written to every once a minute, and how I can reset the system with the watchdog timer. So currently I am compiling the code onto the board. You will see that indicated through the flash of the LED 1 over here. For my output, I am using LED 2. So you will see it flash green. I will start the test now, and you shall see that it will go green at the beginning of the test to indicate that the memory has been flashed, and it turns off after 1 second. Now if we wait 1 minute, we will see it happen again. And there you can see the light goes off again, indicating that we have written to memory once again. Now I will demonstrate the use of the watchdog timer. As you can see, if I press the button, it does not reset. I have to press and hold. You will see a flash of the red indicating that we are going to reset, and shortly after it will reprogram the memory. To show again, if I press and hold, the red indicates a reset, and the green indicates that the memory will be written to shortly after. One last time. Thank you. Just wanted to add a little bit about optimization in my code. So right now I have, I'm looking at the advice tab the Code Composer offers. It looks like most of their stuff that they're running is advice they're giving me is in the drive lib. But for my own code, they recommend using a different a timeout for my while always loop. Now I can understand why this would make sense if you were trying to conserve power or optimize your code. But in this case, since we're just running straight from the laptop, I think it's okay to use this. Another thing that I was looking at was the project properties. And you can see here, as I'm changing the different types of optimization levels, the different suggestions I get. I definitely did take it into my process of programming. And I think it's a cool feature that Code Composer has. Thanks.